we are having, I'm sure, the most shocking lectures during this conference. So let us first invite David Abarca, to give his talk.
Thank you. So I will be talking about the effects of a bow shock from a gas cloud that is intersecting an accretion disk. It's like something like Sagittarius A star or something. Okay. So the motivation behind this is the G2 cloud. If you haven't heard of the G2 cloud, it's a large cloud of gas, or possibly a star with a stellar wind, or even more recently, a tidal stream from a tidal disruption event, or something of the sort. And the idea is, what is this gas cloud going to do that will affect the accretion rate of Sagittarius A star? Because ultimately you're interested in observables. So the idea is that it's a very complicated problem, and there's lots of unknowns involved. So what we did is we considered basically two extreme cases. One extreme case where the cloud is not very dense and ends up mixing with the disk, and then over time it accretes onto the black hole, and that's sort of the long-term effect. And the other extreme we wanted to consider, and that's what the focus of this talk is in the case where you have more of a compact, almost like a bullet. I might refer to it as a bullet several times, but just a very dense cloud that does not get disrupted, passes through the disk, and forms a bow shock in front of it. And the idea is that that bow shock, ideally, will propagate through the disk onto the black hole, and in some way affect the accretion rate. So that's what we wanted to explore. Okay, so to start this problem, we have to consider how the shock wave is formed. And so a bow shock, if you probably know, is formed, is starting from an oblique shock. So in an oblique shock, you just have a uniform wind hitting a wedge at some angle theta. And so then that will form a Mach cone, but more interestingly, it will form an oblique shock. And there's a relation between Mach number, the angle of the wedge, and the angle of the shock. But what happens is, as the angle theta increases, eventually the oblique shock will separate from the body, and you will get a bow shock. And this is the nice round thing that you see when you're talking about these, these bow shocks from clouds and stellar winds and stuff like that. But we use this kind of as our motivation. So the actual problem of calculating the properties of a shock like this is referred to as the blunt body problem. And for this particular case, we wanted to find some analytical solution that would tell us, what the shape of the shock is, and what the the pressure profile and stuff like that is. But we didn't get very far. It turns out most of the papers on the blunt body problem have to do with papers written in the 70s by the Soviets about intercontinental ballistic missiles and stuff like that. Okay, but what we did is we took a solution from a similar situation. So this is from Wilke in 1995, and this is the situation where you have a stellar wind. A stellar wind moving through a uniform medium. It's in I believe it's in the limit of infinite Mach. Oh my gosh, I spelled Mach number wrong. Shouldn't have pointed that out. Infinite Mach number and an infinitely thin shock. And this is the sort of angular dependence to the shape of it. And the idea is if we have an analytical expression of this, then we can see how well we can make predictions about when the shock wave will hit the black hole, etc. But we need to see if this solution is valid at all. So to do this, we run hydrodynamical simulations to test how well the shock works. So the simulation code we used is the code Coral, which you may or may not have heard of. It was developed by Alexander Sadovsky. It's a pretty powerful tool. It's a Eulerian parallel GRR MHD code. But we really, this is really only a hydrodynamic problem. So we really only use the hydrodynamic capabilities. And technically, we evolved everything in general relativity, but our cloud is so far out from the black hole that it didn't really matter. Okay. So the first thing we wanted to set up is just see, how does this analytical solution fit? So the idea is we have, in 3 dimensions, we have just a sphere, so a sphere of gas, and we subject it to a wind. And the conditions of the wind, we picked the wind to kind of replicate the conditions around Sagittarius star. Specifically, what we were focused on is the temperature at 1,000 gravitational radii, because ultimately it's the sound speed, which is depending on the temperature, which affects the shape of the shock. Okay, and then the wind speed corresponds to a parabolic orbit with a periapsis of 1,000 gravitational radii. Okay, so we ran our simulation until the shock reached a steady state, and we found that reasonably, at least for small angles, this analytical solution fit. But once you get out to farther angles, obviously it starts to diverge, and we're in a little bit of trouble here. So one thing we need to do, if I didn't mention already, this is a work in progress. One of the things we need to do is find something better for our analytical solution. But this is what we have to work with right now. And these lines correspond to cuts in density. So you can see here, this is just a fractional rise in density. So you can see at different radii. So you can see basically how much the shock is growing the density. And obviously, as you get farther down at smaller radii, the shock levels out and kind of washes out. But we want to see if the shock will still have any strength once it gets to the black hole. Okay, but this isn't the whole story, obviously, because ultimately we're interested in this cloud-near accretion disk where the conditions are changing with radius. So one of the things we did is we wanted to see what would happen if we changed the wind. So the wind's coming from this direction, and you can still think of the black hole down here. What we did here is we changed the wind velocity to match just the Keplerian rotation of a disk, counter-rotating with the disk in the equatorial plane to see how that changed the shock wave. Obviously, it raised the Mach number, which allowed the shock to more closely follow the analytical solution. But what we're just trying to do is get an idea for what this is going to look like. Okay. But that, again, is not the whole story. So besides the differential rotation of the accretion disk, other things that affect the shape of the shock are the temperature gradient. So as you get closer to the black hole center, obviously the temperature rises. And so as the temperature rises, the sound speed increases. And so the Mach number is effectively lowered as you get closer to the black hole. So we wanted to replicate this effect, and this is where what we did gets a little bit tricky. So instead of applying a temperature gradient, which would have, in this simple setup, which would have caused the flow to diverge because that would have caused a pressure imbalance. What we did is instead we sheared the velocity again, except this time what we did was we decreased the wind velocity, and decreasing the wind velocity, what we hope is reproducing the effect of lowering the Mach number because the temperature is increasing. Okay, and so as you get to the lower Mach numbers, the shock starts to creep up, and I think around 200 or so it actually enters the nearly the subsonic regime. And again, we have you can see how the shock levels out. And then we put those two effects together. We put the two effects together, and they almost cancel out and give us almost what we started with. But if you add both of those effects together, we seem to get a reasonable alignment with our analytical solution. kind of in a roundabout way, which is interesting. Okay. But now what we wanted to do is we wanted to see how this setup sort of fits in with the whole disk. Okay. So we move to the clouded disk portion. Okay. Okay. So so what we did is we took a cloud and we put it onto a stationary disk. And the reason we did that was because we wanted a stationary background where we could actually see the shock, see its shape, and get a good estimate for what the density rises. So we used the equilibrium. It's a general relativistic equilibrium torus from PANA 2013, and it matches the approximate 1/r temperature dependence, which is ultimately what we're after because we're after sound speed. The right sounding. So as far as the density and pressure are concerned, those aren't, those don't really fit the Sagittarius A-star model, but what we cared about was this dependence. Okay, so then in order to actually run this cloud out at a reasonable distance away from the black hole without spending billions and billions and billions of hours of computing time, we just basically cut out the middle. To allow the time step to be large enough because of the way the code works, you need tons of time to resolve the center. So that allows us to do this in some reasonable amount of time, and in the future it will allow us to really, really start probing the parameter space as we start running more simulations and seeing what we can do to affect the shock. Okay, so we take the cloud, we impose it on a parabolic trajectory in the equatorial plane, run the simulation, we see what's happening at the inner boundary of our simulation, and then that we want to extrapolate down towards the black hole. Okay. So this is just a still three-dimensional, just showing you what it looks like, and we have our cloud, and it's on a parabolic orbit through the disk. These are contours in log density. There's only 2 of them, because otherwise we would be able to tell what's going on. You can kind of see the outer shock, which we are not quite as interested in as much as the inner shock. So at least we know that the shock wave is reaching the inner boundary. Okay. Okay, so this are slices in the equatorial plane. And what we've done is, in order to actually be able to see the shock wave anywhere below, say, 2,000 gravitational radii, we actually needed to divide out a background disk. So we took the background disk and divided it out so you could see the shock wave, because it turns out it diminishes quite rapidly, and there's not really anything interesting to see if you don't do that. So here you have the shock just at several different times, basically until if you can barely see it, the shock wave starts to reach the inner boundary of the simulation. And then what we've done is these lines here, we were interested in how strong the shock is, so these lines correspond to these plots here, and I've matched up the times here, match up to these. Okay, so you can see the shock spreads out, it weakens. This is just a fractional rise. You'll notice it's really starting to get low. And this is just a fractional rise in density. What we're ultimately interested in is accretion rate. Okay, so to calculate the accretion rate, we kind of, since we've cut out the whole inner boundary of our simulation, we kind of have to use a proxy for accretion rate. Also, we have a stationary black hole, so there's really no V in to properly calculate accretion rate. So what we said was we're going to assume that the VR, the inner V, is relatively constant with time as the shock passes over it. And we're going to take the accretion rate to be proportional to basically the integrated surface density. So essentially what we're doing is we're just going to take shells and watch how the density, watch how the mass in that whole shell evolves with time. And we do that at several different shells, and these correspond to the radii of the different shells. So the shock first reaches the outer radii, and then it propagates inward, and its strength diminishes, and then its behavior starts to get a little bit erratic at smaller radii, around 500 or 600 gravitational radii. And this here again is the fractional rise. So once you actually add up the whole, so earlier we had probably about 5 to 10% rises near the inner boundary, but once you actually take it to the whole shell, you really are starting to get in trouble, and you get fractional rises that are really only about, that's 0.2%. So we're in big trouble. Okay. But we're interested ultimately in what this looks like at, you'll notice we stopped at our inner boundary at 400. We want to see what it looks like at 2. So essentially what we did is we looked at these plots and we extrapolated, the important parts of them down to the black hole just to see what they would look like. It's not a wonderful extrapolation. We were able to use second order polynomials, but it gives us an idea for what this might be. And in the future, what we want to do is push down our inner radii even further so we can actually get much more reasonable extrapolation. So what these plots are, in relatively arbitrary time units, this is the initial start time, so after the simulation starts, and the pericenter of the orbit for reference is relatively 50. And so what each dot corresponds to is a different radius, okay? And that's the radius of the shell. So we're just basically looking at what's this value, what's this value, what's this value to see, because we want to get an idea for the time scale that this happens in. Okay, and then we also recorded the maximum, the time that the maximum occurred, and then the time when the shock falls down, and then the fractional rise in accretion. So if you follow this fractional rise in accretion, you get about 1.001 fractional rise, 0.1%, almost nothing. It's actually a rather boring result, but at least you know that, so you won't try and do this yourselves. But we did notice that it was relatively spaced out in time. So it's a small rise, but it lasts for a while. So if you take from 65 to 110, and if you convert that to real-time units, that's approximately 2 weeks. So you get sort of a kind of a 2-week period of activity, at least for this particular setup, for this particular cloud, which is interesting. Okay, so basically the conclusions are our analytic solution is not very good, and we didn't really feel comfortable using it to make predictions yet. So we need to work on that. But yeah. So it works at high Mach number, but it really doesn't work for kind of these low Mach numbers that we're working at, like 3 and 4, etc. We clearly saw a strong shock form near the cloud, but once you extrapolate that cloud down to the black hole and take into account the effect of the whole accretion, there's not a whole lot to see. Really minimal rise, like I said, it's about 0.1% for this particular set of parameters that we have, but it lasts a while for this particular setup. And like I said, this is a work in progress that we're still working on, and so in order to make this get some full, robust results, things that we're planning to do, I already mentioned, we want a better analytical solution. And we want to really test the parameter space, see what happens when you vary cloud size, when you vary density, when you change orbital alignment, trying orbits that are in the polar plane as opposed to the equatorial plane, or maybe inclined. As we hopefully get more computer time, we can extend the inner boundary. It'll allow us to run these simulations longer, get better extrapolations. And there's a couple other scenarios that we might want to consider besides just a bullet cloud. And one of those might be a stellar wind, which is a decent candidate, or what I think is probably the best candidate for this G2 cloud is probably like a tidal stream or something like that. So that's our future plans. So thank you for allowing me to come talk about my work. If you have any questions, or more importantly, any comments for me, or any suggestions, I'd be glad to. Thank you.
Tschüss.